Hello viewers, a very warm welcome to my another video. Today I will discuss about the Biot Savart Law. It is a very important law in magnetostatics, and using this law you can calculate the magnetic field, the magnitude of the magnetic field, and also the orientation or the direction of the magnetic field produced by a current carrying conductor. So I start by the by stating the Biot Savart Law, and say this is a current carrying conductor and carrying a current I, and suppose we consider a small portion, that is the current element, small element dl, and we are looking at a particular point P at a distance r from the small element, and if you multiply it with I, it becomes current element. Suppose say this angle is theta, and we want to find out the magnetic field here. Okay, and say the magnetic field is delta B produced by a small current element IDL. Okay. So according to the Biot Savart law, delta B is simply given by a formula which is mu 0 by 4 pi and IDL cross of R by R cube. Okay. Here R can be written as R hat, and R hat is the unit vector in the direction of R. So we can modify this formula using mu 0 by 4 pi, and this will be I of dl, and if you write down like R vector like R hat, then delta L and R hat is simply delta L sine theta, because mod of R hat is 1 and the angle between these two vector is theta, that is A cross B is AB sine theta. So using this law, we can write down like this, and here it is R and this is R cube. So it will cancel out and become R square. So this gets simplified, and this is mu 0 by 4 pi and I of dl sine theta by R square, and the direction is can be calculated using the vector multiplication, that is A cross B. If C is A cross B, then C is perpendicular to both A and B. So here delta L and R is in the same plane. So delta B must be perpendicular to both R and DL. So coming out of the page. Okay. So you can write down like this. This is coming out of the page, the circle, a point. Okay. Now, to know the direction in a better way, we can use the right hand thumb rule. Okay. So just imagine your hand like this. This is your thumb. Okay. And this thumb is always in the direction of the current. Now you wrap your finger like this. Then the direction of your finger, it is the like this gives you the direction of the produced magnetic field. So I will take the several configuration, that is the circular or straight or something mixed configuration of the wire current carrying conductor, and then I will calculate the magnetic field for each of them. And at the end of the session, I will show you practically, that is visually, how this magnetic field can be created and what is its direction. So please stay with me. Now, first of all, you can see here a different type of current carrying conductor. Okay. So before going into that, I just discussed about a circular one. That is, say, if there is a circular current carrying conductor like this and carrying a current of I, and if its radius is R, then how you can calculate the magnetic field at the center? Okay. Center is a symmetrical point, then it's become very easy for us. For other point, we can discuss later. Okay. So you see, here, R is capital R, and I and delta L sine theta. What about theta? Here we see, if you consider this small element here and draw the radius here, you see the radius is always perpendicular to the current element. So angle theta is 90 degree here. So we can write down like this, that is the magnetic field at the center will be mu 0 by 4 pi. Okay. I is here, and this is capital R square, and integrate over dl. Okay, so dl is small portion of that. So if you sum it up, and what will happen, you will get the perimeter of the circle. So this is simply mu 0 by 4 pi, and this is I, this is 2 pi and R, okay, by R square. You can take the limit like this, 0 to 2 pi R. Okay. 2 pi is the angle at the center, and R is the radius. So here I am using A is equal to R theta. Okay. So theta is 2 pi and R is capital R. So total current length, element length is 2 pi R. So just cancel it out. So it will become mu 0 I by 2R. Okay. This is the important result here. And from this law, we can also find out the magnitude and direction of also the magnetic field direction here at the center. So if you see, if you wrap this our right hand with this wire, then here the magnetic field will coming out of the page. So again, this can be represented by a circle with a dot. So now the special case I am taking here is a different type of configuration. As you see here, there are two circle joined by a two section. Now, if you consider the current direction like this, okay, so here it's also I, but here it's moving in opposite direction. Now, this two section is just is directly on this point, so it will not create any magnetic field. Okay, and we just want to calculate the magnetic field due to these two section. Okay, suppose say this radius is A and this radius is B, then the magnetic field for inner section, that is with radius A, that is BA, is simply mu 0 by 4 pi, and again it is A square because radius is same and I is here. We just integrate over dl. Now, what will be the dl? As from above discussion, this integration limit will be 0 to pi into a, because here the total angle created here for this section is pi. So this is pi a. Okay. So this will become mu 0 I by 4 pi a square into pi into a. Okay. So pi cancel out, a cancel out. So this is simply become mu 0 I by 4a. For the section B, we just write down like this, mu 0 I by 4b. Okay. Now you see, uh, for this section, the current for this section of the current, the magnetic field is just going into the page. Okay. But for this section, it is opposite, so it is coming out of the page. So to find out the total magnetic field at the center, we just like write down total magnetic field is like simply uh, BA minus of BB. So the strength of the BA is much greater than the strength of the BB, because here the distance is less and here the distance is greater. So you just take mu 0 I by 4 common, and it will become 1 by A minus of 1 by B. So this is the total magnetic field at the center. Okay. Now I take a very special case here. Okay, the single loop. So it is very easy to calculate. If it is um, carrying a current I, and if this distance is A, then again I can simply write down VA is mu 0 I by 4 of pi A square, and this will be pi into DL. What integration over DL is pi into A. So this will cancel out, and this will become A. So this is simply mu 0 I by 4A. Okay. And here is also the deduction is going into the page, because if you grab this with your hand, then your finger is like this. So in this case, the magnetic field is directly towards the going into the page. Okay. Now I'm discussing, as I'm discussing with the circular section. Now take this type of section here. Okay. You see, here, suppose I'm making an angle of theta, and if this radius is A, then what will happen? Here it is also, these two sections will not produce a magnetic field here at the center. So the magnetic field is only due to this section. So B is something like mu 0 by 4 pi into I, and this is A square, and integration is goes from 0 to A into theta and dl. Why A into theta? Because this angle is, total angle is theta, and this radius is A, so this total distance within this section, the length of this section is A into theta. So this comes out like this, mu 0 I by 4 pi A square and A into theta. So A will cancel out. So simply the total magnetic field at the center is mu 0 into I and into theta divided by 4 pi A. Okay. So depending on theta, the magnitude of the magnetic field can be calculated. So now I am taking another configuration, which is a straight line. As you see, this is a straight line carrying a current I here. Okay. And suppose say this is along say x-axis, and this is along y-axis. So you can write down like this. This is y, and this is the x. And suppose consider a small current element here, dx, and this angle is theta also. So this is the r. So here we can actually make a relation, that is r square will be x y square plus of x square. Okay. Now, if this is theta, then this is pi minus of theta. So again, we can write down like a sine of theta is simply y by r. So we will use these two relation for calculating the magnetic field at the point here. Say point is P. Okay. So here, uh, Biot Savart law, delta p is simply mu 0 I divided by a 4 pi of r square, and I into, sorry, I is already taken, so just delta L. Okay, and sine theta also. Now, here delta L and r square and theta, okay, and these are not actually constant here. So we just uh, change it judiciously as we have taken the wire along the x-axis. So we just write down like this mu 0 I, okay, and 4 pi here, and dl is become dx because it's taken along x-axis, and r square. And so what will be the r square? This is very interesting here. R square is simply, you see, x square plus of y square. Okay. And what will be the sine theta? Sine theta is y by r again, and r is root over of x square plus y square. Okay. So the whole thing is become mu 0 I by 4 of pi, and this is y divided by x square plus of y square, x square plus of y square to the power 3 by 2. Okay. And also dx. So we just want to integrate. Suppose say this is extend from some length, mm, let's say minus L to plus L. Okay, finite length. Now here I am integrating over x square and dx. So just take an integration here and the integration of dv. Okay, the total magnetic field due to this current carrying conductor. So we can just change the integral because it is x square, so it will become 0 to L with 2, but it's minus L to plus L. We can, if you can change the element from 0 to L, and then it has become 2 of I. That is 2 is can be taken here. Now we do the integration first. Suppose say this is the integration. Okay, simply the integration is dx by x square plus of y square to the power 3 by 2. Okay. Now take x equal to y tan theta. Okay. This will become very easy. And this is dx will be simply y sec square theta d theta. And x square plus y square. X square plus y square become x square plus y square. Sorry. X is y square, so y square tan square theta. So y square again sec square theta. So change this integral. Dx become y sec square theta d theta, and this will become y square sec q theta. So this is q. So this will become y square. Okay, and this will become sec theta. So you see, um, y square can be taken out here, and this will become cos theta d theta. Okay, so 1 by y square, and it has become minus of sine theta, and the integration limit. What will be the integration limit here? As you see, the integration, now what will be the sine theta? Because tan theta is simply x by y. Okay, so sec theta is simply 1 plus of x square plus y square. Okay, so cos theta will be y square divided by x square plus of y square whole root. So this will become y by root 2 per x square plus y square. So what will be the sine theta? So sine theta is simply tan theta into cos theta. So y cancel out, it will become x by root over x square plus of y square. Okay. Now there is a very interesting change can be taken here. Suppose say you would just taken out x square, so this will become y square by x square. So this will become x, so x will cancel out. So I just write down here 1 by y square, and this is become minus of 1 by 1 plus of y square x square. Okay, and this will become 0 to L. So this is simply 1 by y square, and this is become minus of 1 by 1 plus of y square by L square. Okay. This is plus of sine theta. This is not a minus of sine theta. Okay. Now, if you just consider the previous result here, so this is mu 0 I by 4 pi, and y is there. So total magnetic field is simply like this, mu 0 I by 4 pi. Here it is y and y square, so y get cancelled out, and simply 1 plus y square by L square, and 2 is here because of the integration. Okay. So this 2 will cancel out, this become this. Now, if you consider a very special case, suppose say L tends to infinity. So our limit will goes from minus infinity to plus infinity. But if L goes to infinity, this thing will goes to 0. So if the length of the conductor is tends to infinity, then we will get mu 0 I by twice pi 1. So this is a very important number. So in this way, you can calculate the magnetic field due to a long current carrying conductor. I think this is very easy, and you understand how to calculate it. And here it is also, you can also find out the magnetic field uh, and the direction of the current. As you see, this is the current carrying conductor. And then again, you can use the thumb rule here. So as you see, your finger direction is moving like this. That is for this point, the current coming outward from the out of the page, and here the current is going into the page. So in the next section, I will show you practically by using very minimal instrument like a wire, like a battery, how to produce the magnetic field, and what is the direction of the magnetic field. It will be the very interesting thing. So please keep watching. Thank you. Now I will show you very interesting experiment here. You see, this is a power source and a coil, and this coil is made up of some insulating copper wire, and it is connected to the positive terminal of the power supply, and the and this end is connected to the negative terminal of the power supply. So current is coming from here, okay, and circling around this loop, and then goes back. So to see the whether magnetic field is produced or not, I have placed a magnetic needle here. The red one is north pole. Now once I switch the power on, you can see that This is deflects. That means a north pole is produced here. That means current is coming from here and then it is moving anti-clockwise direction, and this anti-clockwise direction produce a north pole here, and this north pole actually deflect this magnetic needle. So this is a very simple demonstration of magnetic field produced by a current carrying conductor. So I think it will help you to understand how the magnetic field is generated. And if you change this direction, that means this end is connected to negative and this end connected to positive, then here the current will flow in clockwise direction. So if you look from this direction, then this will be the south pole and this will be the north pole. Thank you.